Hello, good afternoon. Let's start. I'm pleasure to introduce you, Eduardo. Eduardo is a old and close friend of mine. We were from the same class in the university at the Rio de Janeiro Federal University. We concluded astronomy course in 2002. Eduardo obtained the master's degree in astronomy here in the Observatório Nacional with the study on T-Tauri stars. In 2005, Eduardo got a permanent position of teacher in the physics of astronomy and physics at the Federal Technical School, nowadays IFRJ. He started the PhD at the Rio Catholic University in 2005, where he was supervised by Professor Enio Frota da Silveira. At the Catholic University, Eduardo engaged in the new field, the laboratory astrochemistry. During the PhD, Eduardo spent 2 years at the city of Caen in Normandy, France, using the laboratory facilities of Ganil Accelerator. Eduardo then obtained the PhD in 2009 from the Rio Catholic University and University of Caen. More recently, he was CNPq postdoctoral fellow at the NASA Ames Research Center in the US, studying data from the Kepler mission. Thank you, Eduardo, for accepting this invitation. He's going to present us the talk, Kepler mission, planet candidates, characteristics, and Earth analogs occurrence rates.
Thank you, Vinicius. Thank you, Marcelo and Isabel, for the invitation. Thank for all the members of the organizing committee. It's a pleasure to be here, to come back here. I spent about 5 years of my life here in the Observatório Nacional, so it's good to come back and see friends. And as Vinicius said, I'm always change my field. It's good, but also it's difficult because you have to restart everything from the beginning. So and now I will present you my new field that I started a couple of years ago. The project that I'm developing with some friends at Kepler Mission and also from the San Francisco State University. One of the collaborators is from there. And the objective of this mission is to determine the frequency of terrestrial planets, the frequency of terrestrial planets in our galaxy. So I will show you how the mission, how the team, the Kepler team, observed those candidates, those planets, and also how they analyze the data to obtain these planets. This presentation is divided into 3 parts. The first one I will explain the mission itself, the telescope, the orbit, the observation technique, and the second, here the objective is to show you how the telescope is able to observe a large sample of stars, okay? In the second part, I will show you how the data are analyzed to infer the presence of the planet, because we don't see the planet directly. We don't have the image of the planet. So we have to use statistical analysis to infer the presence of the planet. And the third and last part, I will show you some of the steps to compute the occurrence rates of terrestrial planet. Occurrence rates, you can translate this for the frequency of terrestrial planets and the giant planets that orbit a wide variety of stars in or near the habitable zone. We will define the habitable zone rapidly, And the last part, I will show you some results. So let's start from the beginning. The telescope, the Kepler telescope, is a 0.95 meters aperture instrument. Okay, it operates in the optical range that used 42 CCDs in the focal plane. Here, just to see the scale of the 42 CCDs, to photometrically observe approximately 190,000 stars at once, okay? And the field of view of the Kepler is about 115 square degrees. Here I have an image that superimposes the grid of CCDs with the field of view. So this is the field of view of Kepler. Well, the photometer corresponds to the telescope, obvious, and the focal plane with the 42 CCDs with the local detector electronics. The primary mirror is a 1.4 meter diameter, but is limited by the Schmidt corrector of 0.95 meters diameter of aperture. So the primary mirror of the telescope is 1.4 meters, but it is limited by this Schmidt corrector. Well, the field of view, I'm using here the Stellarium app to show you the region. The field of view is across the Cygnus and Lyra constellation. Here, this 115 square degrees. At our coordinates from Rio de Janeiro, this region is very low in the sky, okay? But just to have an idea where the telescope is pointed to at the sky. Well, the Kepler telescope is looking through a direction that corresponds to the Orion spiral arm of our galaxy. And this direction we can detect, the stars that was detected range from 600 light years to 3,000 light years. So the Kepler field corresponds to this direction in our galaxy. Well, the telescope is in a heliocentric orbit, okay? This is enable it to observe always to the same patch in the sky. The orbit is a 372.53 days period. With this orbit was chosen this heliocentric orbit with this period to minimize the torque disturbing in the spacecraft. The telescope, as you could see here, I will repeat this animation. The spacecraft executes 90 degrees rolls every 3 months to reposition the solar panels to face the sun, okay? And during these rolls, it should be stopped, the observation should be stopped to do these rolls. It means that the Kepler continuously observed to the same place, but for only 3 months, continuously. And then it should stop to make this movement, and then we restart to observe for more 3 months. So if you look at the light curve, the whole data, you can see that you have 3 months of observations and then a gap that constitutes this period that the telescope is doing this movement. Each 3 months of observation we call quarters of observation. So it means that during 1 year of observations, we have approximately 4 quarters of observations. Okay?
Eduardo,
Yeah.
how long does it take to make this movement?
Oh, it takes a couple of days. It's not because it's the time to they use this time also to downlink the data. Okay, during this movement, they do this, and also they downlink all the data that is stored in the electronics. Well, the method used by Kepler to detect exoplanets is to search for periodic drops in brightness due planetary transits. Here you can see an animation when a planet crosses the stellar disk, its brightness drop a little bit, and the depth of this transit depends on the size of the planet. For example, Jupiter planet can produce a 1% depth in the light curve of a solar star, a star similar to the Sun, and an Earth planet can produce a 0.01% in the depth. So if you measure the brightness of a star and you detect these signal characteristics of the transit, you can obtain the radius of the planet if you know the radius of the star. So, because I will show some formula that can explain better this, but this depth is related to the planetary radius, but it's related to the stellar radius too. So you need to know the stellar radius to obtain the planet radius. So the main parameter, the principal parameter that Kepler can obtain from the star, from the planet, sorry, is its radius. It can obtain directly from the observations. Well, this was the first part that I present rapidly, the characteristics of the mission. Now I will focus a little bit more in the data analysis, how the team, the Kepler team, vet the signals that they obtain into false positives, because we have many false positives that mimic the signal of a transit, of a planetary transit, or if it is really a real planet. So, this is the light curve of this star. KIC stands for Kepler Input Catalog. Okay, it's a star with magnitude equals to 13, and here we have just the first 3 quarters of observation. The first step is to combine the flux time series from several quarters, because once you observe very many different quarters, you have to stitch all the quarters together to have just a single light curve. Here I'm showing just the result of this first step. All the quarters were stitched together, okay? Well, the second step is to detect the individual transits. Well, for this star is obvious. We have a strong signal of transits in this star, but many other stars do not present a transit very strong like this, okay? So what we have to do is correlate a model, a transit model pulse with the transits of the data to determine if this transit is really produced by a planet or if it is a false positive. So this correlate is sensitive to the matching overall shape between the model and the data. So let's talk about a little bit about the model, okay? So this is the geometric model of a planet transiting a star, okay? A star with radius r asterisk or r star. And we have a planet with radius rp. And here in the bottom, we have the light curve, the schematic light curve of this transit. The solid line corresponds to the transit, to the central transit, a central transit. It means that the planet crossed the stellar disk passing through the center of the star, okay? So we have this solid line here. And the dotted line represents the model, the light curve model of the transit for a planet that crossed the stellar disk with an impact parameter b from the center. So this distance from the path of the planet to the center of the stellar disk is called the impact parameter. That depends on the orbital inclination. The orbital inclination relative to the line of sight. So if I observe a system with an orbital inclination of 90 degrees, it means that I'm observing the system edge-on. And so I will have a central transit. This impact parameter will be 0, okay? A orbital inclination of 0 degrees, it means that I'm observing the system face-on. So I won't have a transit. I can't observe a transit in this situation. So this impact parameter will depend on the orbital inclination. Here we can also see this important parameter. This is an observable from our data, the delta F, that is the transit depth that we saw in the previous slides, that depends on the ratio, depends on the stellar radius and the planet radius. We can define also in this model the total transit duration, that is the interval between when the planet disk touches the stellar disk before the ingress, the transit ingress, and when after the transit egress, okay? And also we can define another parameter, another observable, that is this flat part here of the transit, that is, we just call the transit duration, okay? It is the interval when the planet is fully superimposed to the stellar disk. So we have those parameters here that we can measure directly from our observation, and those parameters are related to the physical parameters of the star and also the planet. Well, you don't have to memorize those formulas, okay? No, don't worry about that. It won't require for the final exam. So I don't memorize everything here. Well, we have 5 equations that describe all the transit light curve. The first 3 equations are called geometrical equations. It is the transit depth, this delta F, that is related to the planetary radius and the stellar radius, okay? This is obvious, this is trivial, it comes from the geometry of the problem. We have what we call the transit shape, that is defined by the ratio between the transit duration and the total transit duration. And we have the total transit duration defined by this equation here. So those equations come out from the geometry of the model. And the other 2 equations are called physical equations. That is the Kepler's third law that link the period of the planetary orbit with the semi-major axis, and also the stellar mass radius relation. With those 5 equations, we can obtain the unique solution for the light curve. So there is only one light curve, one transit model that fits our observed transit. Okay? So what we do is, first of all, obtain those parameters. Those are our observables directly from the light curve. But those observables are obtained by this correlation, because we have to correlate a model transit pulse with each interval in my light curve. So I correlate this pulse with each interval in my light curve, and we can see that in the region where I have a signal, this correlate gives a higher value in the signal, okay? So we have to do that for many different values of the transit duration, because in principle we don't know exactly. For this star, for this particular star, it's relatively easy because I can see the signals, but for other stars the signals are very small, so it's very difficult. I can't see doing a manual inspection if I have or if I don't have a transit there. So I need to do this with an algorithm that will correlate automatically this model with each part of the transit. So I have to use a set of transit durations to show me where I have a great correlation in my light curve, okay? For example, for this planet, for this star here, the transit duration of 3.5 hours produces the best correlation when I compare the pulse with those signals. Well, during this correlation, the algorithm also calculated the noise, because the noise is not stationary, it varies with the duration. So I have the noise calculated for each value of transit duration, and the result of those calculations are that we have 2 time series, the signal and the noise. So we have to do that for each value of transit duration, okay? Of course, that value of transit duration that gives the greatest signal will be the value of transit duration that we're gonna use for further analysis. In this case, for example, we have here the result, the ratio of those parameters, the signal and noise, produces the single event statistics. This is just a fancy name for signal to noise ratio, okay? The single event statistics, or SIS, is just the signal to noise ratio, and here I have this time series of the single event statistics for that star, okay? That is the result of this ratio here, the signal and the noise computed through the time series. Okay, so we have one SIS time series for each model transit used. We have one SIS for each transit duration that we used, and then that SIS time series that presents the highest value will be the time series that we're going to use. For example, for this star, the SIS with the highest value of signal to noise ratio is this one with a transit duration of 3.5 hours. Well, then we have to confirm if the signal that I detect is repeatedly in time. So now we have to use a set of periods, possible periods, orbital periods, to search if this signal is repeatedly in each orbital period that I'm using. So the next step is to fold the cis time series using a set of periods and phase, what it means. For example, for this star, the signal repeats every approximately 54 days. So I divided this time series by 54, and if I have a transit occurring every 54 days, those signals will fall at the same place if I divide all the light curve by 54 days. If I divide it by another period, I won't match all the transits at the same place. So when I do that, I produce another measure that is called the multiple event statistics. They love those names just to complicate our life, but the multiple event statistics is just the signal to noise ratio time series folded by the period that you are testing right now. Well, since for this star has many signals with a high value of signal to noise ratio, 100. This is in terms of the sigma, okay, of the noise. So here we have peaks of 100 sigma. When I fold, I obtain many peaks. But we can see here, the greatest one is the peak at approximately 54 days. The other peaks, they appear because since the signal is very high, about 100 for each transit signal, we can obtain another peaks in other period values with a higher value of significance. Okay, so for this star we obtain many peaks, but we have there the 54 days period as being the period of this transit.
Sorry, so what's the peak at 160 days? What would that be if I wanted to understand how unique the solution is?
Yeah, this is because it's about 3 times of this one.
So it's just a harmonic?
Yes, just an harmonic. Okay. Well, now we have to define a criteria to decide if I continue to analyze this star or if I give up of it, because it can be a false positive or maybe it's just noise that I'm observing. So the criteria was decided before the mission by statistical analysis. Okay, here is the reference, and this study shows that if I have a star with a mass smaller than 7.1 sigma, I can give up this star because I don't have a signal there that corresponds to a planetary transit. Okay? These stars that pass this test, we call another name. This is the threshold crossing event, or TCE. These TCE are those stars that pass this first analysis, this correlation between the model and the light curve, and I have the signal to noise ratio folded by a set of periods with a mass at least one peak. Okay, if I have at least one peak greater than 7.1 sigma, this star is designated as a threshold crossing event, or TCE. If I don't have any peak for any period greater than 7.1 sigma, I can give up this star, okay? And I will concentrate, I will focus just those stars with this criteria here. So for this particular star, the transit duration that produces the highest signal-to-noise ratio is one with 3.5 hours, and the period that produces a highest mass is this one, 54.36 days, okay? So we can fold in all the light curves with this 54 days period to visualize better the transit signal. This is the light curve folded by 54 to 36 days to observe better this transit signal. Well, as you can see, we have many peaks greater than 7.1 sigma. Before the launch of the telescope, this value was just a statistical analysis. They believed that it could reduce the number of false positives to just one false positive to the entire sample of star observed. 190,000, almost 200,000 stars. That was what they expected before the launch. But after the launch of the telescope and the observations showed that many TCEs, many stars with mass higher than 7.1 sigma, are actually false positives. And the reason for that are systematic errors, non-Gaussian noise presenting in the data. Sometimes one very strong event yields signals greater than 7.1 sigma. We could see an example for that particular star, okay? And also we have astrophysical reasons like eclipsing binary star systems and also pulsating stars. Here I have an example of the light curves of many pulsating stars that can, because the first analysis is performed by a machine, it's performed by an algorithm, because we have almost 200,000 stars. It's not possible for a human being analyze each one of those light curves. So the first analysis is performed by an algorithm, a machine, and we have to specify criteria to separate which light curves that we're gonna analyze further, or we can just discard those light curves. Well, the second stage of this analysis, now we have manual inspection to identify these cases. Okay, so those cases, those TCEs, now a team in the Kepler mission is dedicated to analyze each light curve with a signal-to-noise ratio greater than 7.1 sigma and discard those obvious false positives. They are trained to do that when they look at light curves like this. They can immediately discard because they are produced by pulsating stars. Those TCEs that pass these manual inspections now are designated as KOI, or Kepler Object of Interest. I'm telling you everything this because if you go to the NASA Exoplanet Archive website, you're gonna see a lot of those symbols, KOI, TCEs, planet candidates. So you have to know the difference between them if you want to work with the data, okay? So the manual inspection now promote those TCEs to the Kepler Object of Interest, and after that they search for evidence for additional transit. It means if this TCE is not a false positive, it's not a pulsating star or a binary eclipsing, they consider this TCE now, they designate this TCE now as KOI, and then they remove this transit signal and repeat the pipeline, the algorithm analysis to search for another peaks that could be produced by another planet in that star, so in that system, okay? Well, finally, the KOIs are reanalyzed, and some false positives are detected. The most common false positives are the grazing, eclipsing binary system like this one. So the second star pass in front of the star, but not at central transit. So this system is called grazing stellar binaries, and this is very common. Another false positive is the blended stellar binaries. So this system here is a binary, but is in the background. But since the technique used is the photometric analysis, aperture photometry that they used, when you put your annulus here to measure the brightness, the counts of the star, this system here contributes to the brightness of this star. And since this is a binary, it can mimic also the signal of the transit. So they have to discard these cases too. And also brown dwarfs. Brown dwarfs or low stellar masses are also another case of false positives. So this further analysis promotes the KOIs to a planet candidate. So when you see works in the literature that analyze the distribution of planets in the Kepler data, they are using the planet candidates, not the KOIs, neither the TCEs, okay? They are using the planet candidates that pass through all those analyses. Well, I checked there to update those values, and I found that since as of September 2016, we have 4696 planet candidates and 3396 confirmed or validated planets. Well, this is another stage of analysis, because to confirm a planet, planet candidate, you have to realize more observations, the follow-up observations, and measure the radial velocity caused by Doppler effects, and confirm that the movement of the star is produced by another object with a mass appropriate for a planet, characteristics of a planet. So those planet candidates that were observed by this program, the follow-up observations, and had its planet nature confirmed, are now called planet confirmed. But well, another technique to confirm if a planet candidate is a planet or not is the transit time varying. It means that if you see a transit signal and it is repeatedly over time, but not exactly at the same period, this can be a signal that you have a planet disturbed by other planets in the system. Okay? So this is a criteria that can confirm that that signal that you are observing is produced by a planet, okay? So many multi-planet systems were discovered by this technique here. Well, I will show you a plot here before talk about the last topic in the previous slide. Well, this is the distribution of the Kepler candidates, the Kepler planet candidates, here as a function of brightness of stars and planet radius, okay? Those dots here are the confirmed planets by follow-up observations. Take a look at the number of Kepler candidates that you have to confirm by this technique. It's impossible because you need telescope time to do these observations. So what they did recently is to develop statistical analysis to validate the candidate by probabilities, okay? They compute the probability of many astrophysical scenarios to rule out those scenarios if the probability is very small, and then consider that candidate as a planet. With this technique, they could confirm 1284 new planets at once. So you have in paper this one, where 1284 planets were confirmed at once using this probabilistic validation, okay? Because it is almost impossible to confirm the nature, the planetary nature of all the candidates by follow-up observations. Now they are using this statistical analysis to rule out the astrophysical nature of that signal, and then they consider now that planet as, that's why they are using the name. The name is, here you have the planet confirmed or validated. Validated is by this probabilistic validation. Well, the third part of this presentation, I will show you some results of these occurrence rates. It means the frequency of terrestrial planets in the Kepler data, how many planets we have in our galaxy, or at least in that sample that Kepler observes, per star. This is the definition of occurrence rate. The main objective here is to determine what they call the eta Earth, the number of analogs of Earth planets orbiting a G-type star, okay, in the habitable zone. This is what they are pursuing, but it's not so easy. I will show you why it's not so easy. Well, here we have the distribution of all the PCs. PCs is planet candidates. We are working always with the planet candidates, okay? Because we have more samples for that. Here we have the planet candidates and also the confirmed planets. The confirmed planets are the green one. As a function of planet radius in Earth radii units, and here as a function of the orbital period of the planet. So you can see that Kepler has a sensitivity. Now we are able with Kepler to detect planets as smaller as 1 Earth radius. Okay? The question is, those planets are in the habitable zone of its parent star or not? Because the main objective of the mission is to determine this number of terrestrial planets in the habitable zone. But those terrestrial planets are also scientifically interesting. Well, this is the distribution. And now what people are doing is to focus in one range of this distribution. I will show you some works that focus in this range here, okay, from 50 to 300 days of period and 1 to 4 Earth radius. So it is a small box here in this distribution. Well, this is the distribution of the observed planets, Kepler observed planets, as a function of planet radius, the difference for periods greater than 50 days. So we are cutting this distribution here from 50 days and greater, okay? And in radius we are from 1 to 4. So I'm showing a small range of that distribution. And when we see this distribution, we can see that we have a maximum value of planets here around 2 and 2.5 Earth radius. This is the super Earth. So, we can see that the number of planets increase when the distribution increase from Neptunes to super Earths, and then after that we have this decrease of the number of planets. So this decrease is real, or it is just a observation bias? Okay, so the number of smaller planets are really smaller than this peak here, or maybe it can flat, or even it can continue to increase. To answer this question, we have to calculate the sensitivity of the mission, the whole mission, not just the photometry sensitivity, but also the capability of the whole pipeline to detect the transit signals. We have to calculate the sensitivity of the emission to see if this observed distribution here is really a bias or it is real. Okay, if in nature produces more super Earths than the other planets. It is interesting because here in the solar system we don't have super Earths, right? After Earth we go directly to Neptune. Well, I will show you here the samples that we have to cut, we have to choose to analyze. This is the sample of Kepler stars observed, okay? And what everybody do is to cut, for example, GK stars. The selection of stars here are of spectral type G and K. For GK stars, and for this range of period in radius, here we have from 50 to 300 days, and 0.8 to 2.5 Earth radius. I mean, we are looking exactly for this region here. Okay, we are analyzing exactly this region here of planets, candidates. We have those candidates here. The number drops to 100, 200 planets. Only if I consider GK stars and those ranges of period and radius. We have about 150 stars. I don't remember exactly the number of candidates that we have if we do those cuts here. Okay. Superimposed to the position in this diagram of the planet candidates, there are some contours that represents the sensitivity of the mission. It means that for this contour here, the mission is able to detect 1% of planets. Okay, just the probability to detect a planet with those values of period and radius is only 1%. And this contour here is 50%. It explains why we have a lot of detections here in this corner and nothing here. Okay, this is actually a bias of the telescope and the analysis. So to answer this question, we have to correct the observed data, the observed distribution of planets to this sensitivity. I made some calculations also about this sensitivity in a wider range of period. Here I'm going through until 700 days, and also in planet radius. Here I'm going from 0.3 Earth radius until 20 Earth radius, okay? And we can see the same patch, the same behavior. Here we have strong sensitivity, strong probability to detect a transit for giant planets with smaller orbits. And here I draw this black region here because this black region has a probability of detection smaller than 10 to the minus 5. It means that 0.001% to detect a planet, okay? Well, when we correct the observed distribution, this is again the radius, the number of planets per star, okay, as a function of Earth radius. We can see that instead of decrease when I look through smaller planets, the distribution increases. What it means that we have more terrestrial planets and smaller planets than giants in the Kepler data, if we consider all the sensitivity bias of the telescope. This distribution I cut for orbits is smaller than 50 days, and here for orbits is smaller than 250 days, okay? And those cuts in orbit produce the same result, more or less the same result. The distribution increases for smaller planets. So we have more small planets than giant planets in the nature. Now I'm show you the distribution corrected, okay? The corrected distribution by the sensitivity, but as a function of period for 4 different planet sizes. Here I put just the Earth planets from 1 to 2 Earth radius. Here the super Earths. Here the Neptunes, and here the Jupiters. And here we have the same axis scale. Okay, so comparing the distributions, we can see that we have more Earths relative to super Earths, Neptunes, and Jupiters. And also, what we can see is that the corrected distribution of planets increase with orbital period. So the nature produces, it seems that it produces more terrestrial planets and at longer orbits. Here my orbit is going until 250 days. Okay, 250 days. I cut it to 50 days. And another difference between those results to the first one that I show you, because this cut here, I made other cuts. You see that the range of radius and periods in my results are bigger, okay, are more extended. And I used G, K, and N stars, okay? This cut here was made just for G and K dwarfs. Okay. Other results that we can find in literature is if we now analyze the planets, the planet distribution as a function of the spectral type of stars. So, if we take just G stars, the corrected planet distribution is given by this yellow curve. Here, again, the range is from 1 Earth radius to 4.5 Earth radius, okay? And the red one is for M-dwarf stars. What is interesting of this result is that for M-dwarfs, we have more terrestrial planets and smaller planets than G-dwarf stars. But relative to Neptune's, it seems that around the G-dwarf stars, we have more, G-dwarf stars produces more Neptunes than M-dwarf stars, okay? This is for planets with smaller orbits, around 20 to 50 days. If we look at longer orbits, from 50 to 150 day, we can see that this difference here decreases a little bit. It's almost the same, but still we have M-dwarf stars with more smaller planets and G-dwarf stars with greater Neptune's planets than M-dwarf. So those results could be interesting for people that work with modeling, with planetary formation, because they have to explain this behavior, why M-dwarfs are producing more terrestrial planets, or in G-dwarf stars we are looking at more Neptunes than around M-dwarfs. So the first time we are obtained those results, because before Kepler mission we didn't have any idea of how is this distribution of planets. Now we have an idea how those planets are distributed around those stars. But speaking about the astrobiology, what is interesting for the astrobiology is how many stars, how many planets we have in a good position for habitability. I know that there is great discussion about what is this habitable zone. Here I put one definition, that is the range around a star within which a planet with an atmosphere can support liquid water on the surface. This range is defined using the system Sun and Earth, but can also be computed for other systems, okay? And here I put some distances as a function of spectral type obtained from this work here of the habitable zone, okay? The habitable zone around a F star is far away from the star and very close for M stars, and that it explains why people are very interested in M-dwarf stars, because since the telescopes are sensitive to with planets with smaller orbits, it's easier to detect a planet in the habitable zone around M dwarfs. Okay, that's why the M dwarfs are being studied very systematically now. Well, we can do the same plot of the distribution of planets, the planet candidates, but using, instead of the period, plot here the insolation flux. Okay, here still we have a planet radius. Here this dotted line is just to put a limit in planet radius that here we have, below this line, we have more probability the planet is terrestrial, is a rock planet, okay? And this work was the first one produced by the Kepler team, where all the analysis was performed automatically, without the manual inspection. They create many routines to substitute the manual work, and then the disadvantage of manual inspection is that the sample is not homogeneous. The analysis is not homogeneous because we have the one person analyzing one light curve and another person analyzing another light curve. So with this routine, they could produce now a catalog homogeneous. Okay, all the analysis homogeneous. Well, I will show you just for fun some systems that could be interesting for astrobiologists. Here is the insolation flux as a function of the spectral type, the surface temperature of the star. The Venus, Earth, and Mars are represented here for reference, and the habitable zone also are presented here. And well, I took some examples here that Kepler 186f, Kepler 62f, and Kepler 452b. Because here we have the smallest planet. Here we have a planet around in the habitable zone around the K star. And here we have a planet around a G star, and more or less at the same position of Earth, but actually it is a super Earth. And let's compare those systems. The first one is Kepler 186f. This is almost the same size of Earth, okay, with a period of 129.9 days. Here is the system comparable with the solar system. Here is Kepler 186f. Look that its orbit is more or less the same of Mercury, but it is in the habitable zone because the star is a M dwarf. Okay. The mass of this planet, well, it's uncertain, but 0.32 Earth mass could be is the theoretical value for pure ice, and 3.77 Earth mass for pure iron. Okay, and here you have the properties of the host star. It's a M1 spectral type, half the size of the Sun, with this temperature here, and it's very close, 150 parsecs of distance. Maybe this system will be a target for the TESS mission that will search for exoplanets around the nearby stars. Okay. The second one is Kepler 62f. Here is the system. 62f is the highest orbit for the system. It's a very compact system. Here is the Earth. Okay, so its period is about 267 days. It's 1.4 Earth radius planet around a star which spectral type is K2, okay? And the distance is around 1200 light years for this planet. And the last one is the Kepler 452b. Is 1.6 Earth radius in a orbit very close to the orbit of the star, 384.8 days. A little bit longer. That's why its position is here. It means that relative to the insolation flux, it is a little bit higher than a little bit higher than Earth. Okay, 452b, and here the host star is very close to the Sun, a G2 spectral type, more or less 1 solar radius, with temperature very similar to the Sun, and at this distance, 1400. Well, if we now do the same analysis of the occurrence rates, it means the number of planets per star, considering each type of star, G, K, and M, and considering just only planets in the habitable zone, we can have this result. This is just for habitable zone planets, okay? A G-type star, considering, you know that the habitable zone, we can define a conservative habitable zone and an optimistic habitable zone that is more extent, okay? Looking at the conservative, because in conservative habitable zone is more interesting for astrobiology since it considers the presence of the oceans, okay? The G-dwarf stars has a occurrence rate of terrestrial, and also I'm considering terrestrial planets, okay? Has a 0.08 planets per star, okay? K stars 0.03 and N stars 0.008. If we go to optimistic habitable zone, we have the region is more extent, we have more samples in this region to analyze, and then we have those results here. Well, the problem of these results is that many different people is obtain your own results, and they are very different. I put here some results of the occurrence rates. There is a great debate about the methodology to obtain those results. But you can see that the occurrence rate is not greater than 1, okay? It means that if we can say about the occurrence rate, an average occurrence rate for terrestrial planets, for either Earth, we can take the number 0.15 or 0.2 for the number of terrestrial planets in the habitable zone per star in our galaxy. The Kepler team is focusing in this calculation, in this result, because this result will guide future missions that will search for biosignatures in the atmosphere of planets. Okay, so that's why they are very interesting in this result to guide the new missions, to optimize the telescope time to observe directly these planets and find these biosignatures in its atmospheres. So, thank you very much for your attention.